Section 1.2 Row Reduction and Echelon Forms. We'll begin this section with some terminologies. Non-zero row, matrix is a row with at least one non-zero entry. If you look at a row, so that there is at least one non-zero value, then it is a non-zero row. A leading entry of a row is the leftmost non-zero entry. Once the leading entry has a value 1, then it is a leading 1. Now we define echelon forms. A rectangular matrix is in an echelon form if it satisfies these three conditions. All non-zero rows are above any rows of all zeros, so that zero rows will go down. Each leading entry in a row is in a column to the right of leading entry of the row above it. That means that leading entry, the positions are going down and right. All entries below leading entry in a column are zeros, so that once it becomes an echelon form, then also if we try to see non-zero entries, then it looks like an echelon like that. So outside the values are 0, and particularly below of this region is 0. Then we say the matrix is in an echelon form. Now, an echelon matrix, a matrix in an echelon form, becomes row reduced to echelon form or reduced to echelon form if it additionally satisfies these two conditions. The leading entry in each non-zero row is 1, so the leading entry becomes now leading 1, and each leading 1 is the only non-zero entry in this column. So except the leading 1, the column must be empty. Then if these two extra conditions are satisfied, then it is a reduced echelon form. Okay. Let's check if the matrix is in echelon form. If not, put it in echelon form. It's not echelon form because, first of all, this first statement is violated. Non-zero rows are above any zero rows. But here we have a 0 row on top of the matrix, so that we interchange, okay, the rows. Okay, here, from this one, we interchange. Now, we put this on the bottom and we move up for the other two rows. Then we can reach at here 1, 2, 0, 0, 1, and the second row will be 0, 0, 3, 0, 4, and the final one will be now 0, 0, 0, 0, 0. Right? Okay. Now this is it satisfies these first three conditions. Now this is a leading one, and this is a leading entry. Leading entries are here appearing and down and right, so that this is in echelon form. However, now it's not reduced to echelon form. The leading entry must be 1, and by using scaling operator, we try to get leading 1. It's 1, 2, 0, 0, 1. First row is not changing. For second row, we'll try to multiply 1/3, and then there will be 0, 0, 1 and 0 4 over 3, and the final row is a 0 row. Okay, we recheck this one. Now this is leading one and leading one, and so here this one is satisfied. Now the leading one is the only non-zero entry in its column. Here you can see that except this one, these two are 0, except this leading entry, these two are 0, so that the final condition is also satisfied. So it is reduced to echelon form. Okay. Verify whether the following matrices are in echelon form. Reduce the echelon form. Okay, for this one, now this is a leading one, and this is also a leading one, and here except the leading ones, everything else in those columns are 0, and so that it is in reduced to echelon form. How about this one? This is a leading entry, leading entry, leading entry. So it is not even on echelon form. Okay. And this is a leading one and leading one. Except the leading one, the columns are 0, so that this is in reduced echelon form. Everything is satisfied. How about this one? Leading one, leading one. Of course, this is a leading entry. So leading entry is on and down and right. So it is in echelon form. However, it is not in reduced echelon form. These leading ones, this must be leading one, and then except the leading ones, everything else must be 0, right? Okay, now we go to the fifth one. This is now leading one and leading one, leading one. Leading entry is go down and right, so it is in echelon form. However, now these are non-zero, so that it is not reduced echelon form. How about this one? This is a leading entry, and leading entry, leading entry is not in down and right format, so it is not echelon form. Okay. Of course, once it's in reduced echelon form, then it's automatically echelon form. Okay. Each metric is row equivalent to one and only one reduced echelon form. That means that once you are reaching out from a given metric, reaching to reduced echelon form, then it's always the same. But echelon form is not unique. For example, here, this is an echelon form. You may multiply 1/4 for that one, then this becomes a leading one. However, now here the original one and this one is different, and then echelon form can be more than one. However, if you reach a reduced echelon form, it's unique. Only single reduced form, reduced echelon form exists. Okay. Pivot positions. A pivot position is a location in A that corresponds to a leading one in the reduced echelon form of A. We start with this metric, and we can reach at the reduced echelon form here. Now, this is leading one, and this is a leading one, this is a leading one, so that the pivot positions are here, locations in A, So this is the corresponding location is this one. So this is a pivot position, and also this is a pivot position, and also this one is a pivot position. Okay. A pivot column is a column of A that corresponds a pivot position, so that once a column has a pivot position, then it is a pivot column. So we have this one and that one and that one are pivot columns. That is the definition. Once a matrix is in an echelon form, further row operations do not change the positions of leading entries. So once you are reach at on echelon form, then already at the moment, already the pivot positions are decided, and further operations for reduced echelon form is not changing the pivot position, and just it makes the leading entry to become leading one, and then also except the leading one, the columns will be emptied. Okay, here we define basic variables and free variables. In the system AX equal B, the variables that correspond to pivot columns in the augmented matrix are basic variables. Once it's not basic variable, then we call it free variables. Okay, let's consider this example. For the system of linear equations, identify as basic variables and free variables. Okay, we may start with its augmented matrix. Here, first collect the coefficients matrix. Okay, that is now -1, -2. And this is also third one is 0. And from here, 0, 0, 2. And from the third equation, we have 0, 0, 3. And right hand side is -3 and 4 and 6. This is the augmented matrix. From here, now we multiply -1 for the first one. Then there is 1, 2, 0, and 3. And then for second one, we may try to divide by 2. Then there is 0, 0, 1, 2. Right? How about for the last one, we multiply 1/3. Then there is 0, 0, 1, 2 again. Right? Now, to make a reduced echelon form, first you have to make an echelon form. We have to eliminate the below of this pivot. And now, because the same row, and after subtraction, it will become 0. So that we reach it here. And there is 1, 2, 0, and 3. The first row is not changing. Of course, over there, the second row is remained not changed. And then the final row is 0 here now. This is pivot, and leading ones, and except the leading ones, everything else is 0. Now that is reduced to echelon form. And the position here, this one, that one, is pivot position, so that the pivot positions are this one and that one. And these are pivot columns. And from the definition, the basic variable is the variables that correspond to pivot columns. So that this one is corresponding to x1. Now, this one is corresponding to x3. So that we have two variables, x1, x3, for basic variables. Of course, here x2 must be free variables. Okay, that one is free. Okay. Now here we'll consider the reason why we call it free. Okay, let's try to solve the problem. Okay, it starts from this linear system, and by applying elementary row operations, we reach this one. And so that the solution for this original system and the solution of this transformed system should be the same. Okay. Now we rewrite this one into the algebraic equations. Then that will become now x1 plus 2x2 equal 3. And the second one will make x3 equal 2. Okay, we have this one. Now we keep basic variable in the left hand side and every constant or free variable to the right side. From the first equation, we have x3 equals now 3 minus 2x2. From the second equation, okay, I made a mistake here. This is not x3. Okay, that is x1, right? Okay, now from this one, now x2 equal 2. Okay, we'll try to put one more line here. Oops, that is x3. Now, x2 is a free variable, so that if we try to write down x2 equal something right hand side, the only choice is just x2, right? The reason we are working in this way is that once we try to find a solution, then we have to find for every variable, the values for every variable. So we put here x1, x2, x3 all together. Now we can rewrite this one in this way. Here, left hand side is x1, x2, x3. Okay, this vector is same as the constant part for that one. You may consider this one as now 0 plus, and that is plus 0x2. You may think in this way. Then now we can write this one easily in this way. That is now 3, 0, 2, a constant vector, and for this portion, every year x2 is involved with the vector minus 2 and 1 and 0. The coefficients of x2 is minus 2, this is 1, this is 0. So here, this is a solution. But in this solution, x2 can be arbitrary. Now, there's no restriction for x2 to be any number. So x2 can be an arbitrary number. So that's the reason we call it free. And for any choice of x2, the right hand side will be a solution for given system. Okay. Here we have the row reduction algorithm, and here we consider steps to reduce the echelon form. Start with the leftmost non-zero column. This is a pivot column, and the pivot is at the top. So start with a non-zero column. Then the first non-zero column, leftmost non-zero column, will be a pivot column. Choose a non-zero entry in the pivot column as a pivot, and if necessary, interchange row to move the non-zero entry into the pivot position. And by using the row replacement operations to make the below of the pivot position 0. And in this computation, we may ignore rows and columns containing the pivot and ignore all rows above it. Just we try to empty the below of the pivot. And we repeat this 1, 2, 3 for after moving each time to the right side, and try to make the below of the pivot 0. And then now for leading entries, by using scaling operation, the pivot must be changed into 1, and then the leading one above of the leading one must be eliminated. Okay, that is the algorithm for row reduction. Okay, let's see this example. Once you read these statements, then it's not easy to understand. So through this example, you can understand it more clearly. Row reduce the matrix into reduced echelon form. Okay, A is given here. Now, here number 1 over there, start with the leftmost non-zero column. In this case, this is non-zero column, so that it becomes a pivot column. And at the top here, over there, that is the pivot position. But it's 0, so that we have to change. We have to choose here non-zero entry and interchange to make it non-zero. So we chose here third row and first row and third row interchanged. So we have this one. Just simply we interchange the R1 and R3. We recheck that one. Of course, R2 is not changed. And then by using this pivot, we try to eliminate the values below 0. So that is here, number 3 here. So here twice of R1 is added to R2, then that will become 0. That is exactly this result. And here now it becomes the pivot position, and we can do it here. Just okay, 3 over 5 can be multiplied to the row, and we can eliminate. And then it's a little bit complicated, so that we apply scaling, so that we simplify this second row. So we reach that one. And then now we have to eliminate that one by adding 3 times of R2. Then we reach that one. Okay. And here, now, this is, now, so that we reach here echelon form. This is the leading one, leading entry, leading entry, leading entry. Leading entry is moving down and right, so that, and below, every value is 0, so that this is in echelon form. Okay. Now, so here we finished up to here number 4, and we have to make in reduced echelon form. First, we multiply minus 5 for the last one, then it will become 1. And then, so that it will become 0, 0, 0, 1, 0. 3 times is added to make it 0. And 9 times is added to make it 0. So that above the pivot, change it into 0. So we have here 1, 0, 0. Now, for this leading entry, we have to eliminate above here. So that R1 is replaced by R1 minus 4 times of R2. Of course, that will become 0. And the result is here, 1, 0. And 4 times is now subtracted so that it will become minus 3. 4 times minus 12 is subtracted, which means 12 is added to become 5. So we reach at this one. Now, here this is leading entry, leading entry, leading entry, and except this leading entry, everything else is 0 in each column here. So it is in reduced echelon form. Okay, in this way, we apply the elementary row operations to get reduced echelon form. Here, in 1 to 4 is the forward phase. That means now we reach to an echelon form, and then now above the pivot must be emptied. That is now backward phase. So in the above, the combination of steps 1 to 4 is called the forward phase of the row reduction, while step 5 is called the backward phase. Okay, this is the end of the first part of the section. Thank you.